Hello and welcome back again to this online course on fundamentals of composites and cellular materials. So, for last few classes, so we were talking about interface in composite materials, and then we started talking about different examples or case studies where the interface in metal matrix composite and ceramic matrix composites have been discussed. In the last class, the examples I gave, there were two examples I gave. One was on MMC, where the matrix was aluminum matrix, and then it was reinforced with three different kind of reinforcement particles, and we discussed how would be the interface in these three cases. Similarly, we talked about a ceramic matrix composites, particularly SiC composite. So, there are also two different kinds of SiC fiber were used, and then we discussed there that if we used different kind of same composition, but different kind of fibers coming from different processing routes, then how the interface could change even if you do not change the matrix and reinforcement. So, in today's class we would like to continue in the same line, and I will be giving two examples again. One would be on MMC, other one would be on CMC, and the first one, as you can see, we will talk about copper CNT composite, and the second one would be a CMC, where ZrO2 or zirconia is the matrix and which will be reinforced with niobium, a metallic reinforcement, and then we will see how would be the interface in these two cases. So, let us start. So, the first example, as I mentioned, is copper matrix composite, which has been reinforced with carbon nanotube, and in this case carbon nanotube has been functionalized. Now, as you understand, carbon nanotubes are nanoparticles, right. So, they will be having a very high amount of surface energy because of their very small size, and because of this high surface energy they would be having a high agglomeration tendency. So, that is a problem, because if the reinforcement particle gets agglomerated or if they do not get homogeneously distributed throughout the matrix, then you do not get the required properties. Okay. So, that is why this functionalization comes into picture. So, that the CNTs are functionalized here to improve dispersion in the matrix. So, the matrix is, as you can see, spherical copper powders, and then reinforcement is CNT and nickel coated CNT. So, I will discuss why this nickel coated CNT has been used. Now, the primary problems when you try to use carbon nanotube, such small nanoparticles to reinforce metal matrix, the first problem, as I was mentioning earlier, is to achieve homogeneous distribution of CNTs in the metal matrix. And as I was mentioning, that being nanoparticles, they will be having very high surface area, that means very high surface energy, which would ultimately lead to agglomeration of such nanoparticles. So, dispersion is a homogeneous dispersion is a huge problem. And the second problem is that carbon nanotube and metal matrix, generally they do not form any kind of chemical bonding at the interface. So, basically it is relied mostly on the mechanical bonding. So, how the bonding could be improved, or how the wettability between CNT and metal matrix could be improved, that is another area of research. So, we will discuss about these 2 points as we go along. Now, how we are talking about functionalization of carbon nanotube. So, let us see how it has been done. Now, CNT has been taken, basically CNT has been synthesized by chemical vapor deposition technique, and then it has been acid treated by H2SO4 HNO3 mixture. Okay. Now, this acid treatment is a process of functionalization, it is called chemical functionalization. What is the role of acid treatment here? Now, once the CNTs are treated with high concentration acid, what happens at an elevated temperature? What happens? Defect density increases on the surface. or the surface gets basically aged, there will be open carbon carbon bond, and in those open carbon carbon bond either hydroxyl or some other oxygen containing functional group would be attached, and that would help ultimately in better wettability or better mechanical bonding during making the composite material. So, that is the reason acid treatment or chemical functionalization was done on CNT. So, ATCNT means here acid treated CNT. Obviously, it has been dried, and then you see the last step says using electrolysis deposition method to deposit nickel on the surface of the preheated CNT. Okay. So, that is being called as nickel CNT. Now, why this nickel coating has been done? Again, ultimately it is a metal matrix, and if you have a metal, another metal, then there will be better bonding in terms of metallic bonding. So, this nickel thin film is deposited, or nickel nanoparticles basically has been deposited on the CNT, so that it improves the wettability when it is being synthesized as composite material. So, there are two treatments you can see here clearly. One is acid treatment or chemical functionalization, that would lead to defect density increase on the surface, that would ultimately will lead to better bonding. Similarly, nickel thin film or nickel nanoparticles has been deposited on the CNT surface, that would also lead to better metallic bonding during synthesis of the composite material. So, now once this CNT has been prepared, which they are calling as nickel CNT, next is it has been mixed with copper particles by ball milling, and then this powder mixture has been sintered by a special technique called spark plasma sintering. It is an advanced sintering technique. In my one of my last classes, I have actually mentioned a little bit about spark plasma sintering. So, it is an advanced sintering technique where sintering can take place at very less time and lower temperature than conventional sintering temperature. So, that is the advantage of SPS, and it will be having a very high heating rate, and because of its particular technique, particular mechanism, SPS leads to very good densification in very less time. And once it has been done, once the sintering by SPS or spark plasma sintering has been carried out of this powder mixture, then the component has been cold rolled, further cold rolled basically to even improve densification. Whatever porosities are remaining even after doing the sintering, if you want to get rid of that, then you go for secondary processing. In this case, they have carried out cold rolling. So, ball milling of the powder particle mixtures, Cu particle and nickel coated CNT particles, they have been mixed together by ball milling, then it has been sintered by spark plasma sintering, and then subsequently it has been cold rolled. Okay. Now, let us look at the microstructures. So, what we are seeing in this particular TEM images is basically the change in carbon nanotube as it goes through different treatments, from acid treatment to nickel deposition. So, initially you can see here this one is a basically pristine carbon nanotube. So, you can see the multi-wall carbon nanotube, the multi-walls of this carbon nanotube, and then the inside is hollow, and what you see here, they are quite parallel graphene sheets. So, it is quite defect free structure. The moment it is acid treated, what you are seeing here, there is increase in defect density on the surface. So, the surface gets aged, and that leads to open up this carbon carbon bond, and then some hydroxyl ions, the groups could get attached here, oxygen containing hydroxyl groups or other groups could get attached here, and that would lead to this kind of defect density increase on the surface. You also can see that there are actually one wall is getting above another wall. So, those kind of defects are generating once the acid treatment is done. Okay. And the next step was to deposit nickel particles, nanoparticles. So, you can see here nickel has been deposited by electrolysis plating, and it has covered most of the area, but obviously there are some areas which are not covered also. So, the nickel deposition is not extremely uniform or very uniform, but it more or less covers the surface area of the acid treated or functionalized carbon nanotube. And I think that is what has been mentioned here, that the walls in case of pristine MWCNT are continuous and parallel to each other, as you can see here clearly parallel to each other, and then obviously it shows quite high crystallinity. The moment it has been acid treated, you can see here that ultimately there is increase in defect density on the surface, and then once the nickel coating has been done, and the nickel coating was carried out basically to improve the wettability, and you can see here that the surface now becomes quite roughy, you can say. The roughness of the nano roughness of the surface has increased because of the nickel nanoparticle deposition, and again you can see that the nickel nanoparticles have not been completely uniformly deposited, but ultimately these nickel particles, nanoparticles of the nickel coating would improve the bonding in terms of metallic bonding with copper once it gets sintered or once the composite material is being synthesized. All right. Now, let us move on and let us see what happens with carbon nanotube further. So, what we are seeing here is Raman spectroscopy. Now, I have mentioned earlier also Raman spectroscopy is a basic technique which is used a lot to understand the defect density in graphene layers or in carbon nanotube, graphene nanoplatelets. Okay. If you want to know how is the structure or how is the crystallinity in the structure, what kind of defects are there, then carbon nanotube, this Raman spectroscopy is a technique which is practiced a lot. Now, what we are seeing here, there are 3 different spectra, and the first one, this black one, is basically from the pristine CNT. You can see that, and you can see there are 2 peaks, one is called D band, other one is called G band. G stands for graphene band and D stands for the defect density band, or defect, if there is some defect in the structure, you will get this peak. So, you can see the pristine carbon nanotube is quite crystalline because of its high peak, high peak intensity for the graphene band. Now, once it is acid treated, you can clearly see that this graphene peak intensity has been reduced significantly, or in other way you can say the intensity of the defect band has increased now, right. That means the idea of creating defect on the surface by doing acid treatment or chemical functionalization is actually successful here. And then once the nickel has been deposited on that acid treated CNT, what you are seeing here is that again there is increase in the G band or G peak. Why this is happening? Because the moment nickel gets deposited on the surface, it covers a lot of defect density on the surface of this carbon nanotube, right. And that is why again this G intensity, G peak intensity has increased. Okay. Now, let us see once the powder is mixed. Okay. Now, see, this image is not coming from any composite material, but it is a composite powder. The powder has been mixed by ball milling, and those after mixing by ball milling, how are the carbon nanotube distributed inside the with the copper particles, that has been shown here. So, you can see what you are seeing here basically is that this is for the first 2 images for 1 volume percent CNT, and the next 2 images, these 2 images C and D are for 2 volume percent CNT. Okay. And then I will come to the second one, third, this fourth, fifth and sixth later. So, if you compare these two, what you are seeing initially when you have 1 volume percent CNT, CNTs are well distributed, as you can see clearly. Okay. These CNTs are obviously acid treated CNTs. Now, you can see those are nicely distributed. Yes, you can see some clusters, but more or less they are distributed well in the matrix powder, with the matrix powder. The moment you increase to 2 volume percent, because of higher volume percent of CNT, now there is lot more agglomeration. Even these are functionalized, but still 2 volume percent CNT is quite high amount to get rid of agglomeration problem. So, you can see there are in between the copper particles here also, in between the copper particles, those carbon nanotubes gets agglomerated. Okay. And these 2 images are coming from nickel treated CNT or nickel deposited acid treated CNT. So, here actually even at this is for 1 volume percent and 2 volume percent, you do not really see any carbon nanotube here, like open carbon nanotubes are not being seen here, okay, or naked carbon nanotubes are not that well visible here, and that is happening because now the carbon nanotube particles have been coated by nickel coating. So, that is why those CNT particles are not much visible or not well visible in these two cases. When it is 2 volume percent, there are still you can see those particles a little bit, but you do not really see as you were seeing in earlier cases when they were not deposited with nickel. Okay. So, what is happening here from 1 to 2, when you have higher amount of CNT, there is more agglomeration, and then once it is treated with or deposited with nickel, then you do not really see them individually as carbon nanotube particles or carbon nanotube fibers. All right. Now, let us see once it has been sintered and once then it has been in this case it has been cold rolled, what happens with the microstructure. So, you see here the microstructure has been shown here, the TEM images. So, few things are very clear here. These two are for these two images are for 1 volume percent and these two are for 2 volume percent. So, the number density of CNT is increasing obviously, as you can see here there are a lot of CNT clusters, and these are you can see these clusters here. Okay. All these clusters are more when it is 2 volume percent CNT. Remember here these CNTs are acid treated and nickel coated both. So, now we are talking about CNTs which are being used, these are acid treated as well as nickel coated. So, the first observation, as I mentioned earlier, that the volume percent or the number density of the CNTs are increasing as you go from 1 to 2, no rocket science there. Another very important aspect you can see here is that because of the rolling now, the CNTs are getting aligned in the rolling directions. You can see here these CNT clusters are getting aligned with the rolling direction. You can also see here as well. Okay. So, the CNT clusters or the CNTs also, all those are you can see here clearly those CNT clusters and CNT particles, those are actually getting aligned on the direction in the direction of rolling. So, that is what you are seeing from here, that nickel CNT clusters are forced to extend along the rolling direction due to the plastic flow of the copper matrix. Because of rolling, there is plastic flow of copper matrix, and that leads to alignment of the carbon nanotube particles in between the copper particles in the direction of rolling. Okay. Now, as we understand this point, now let us look at the interface, because that is what we are interested in. How exactly is the interface in this case? So, you can see here the interface between copper matrix and carbon nanotube. It is quite clean interface, that means there is no interfacial product formation, as is like copper carbide or no other oxides are not really forming. You can see here it is quite clean. You also can see here in this FFT image that this this T shaped actually this marks are basically showing some presence of dislocations. Now, this is very interesting. Now, from where these dislocations are coming? So, the dislocations could come during sintering if there is mismatch in coefficient of thermal expansion, or ultimately that would lead to some kind of residual stress generation, and this residual stress would lead to generation of dislocations, and most likely these dislocations are coming from those residual stresses at the interface. Now, here if these kind of dislocations are being present, which could be because of residual stress generation at the interface, that means this residual stress is not getting released, or in other way the interface is quite adherent, then only this kind of residual stress will be remaining there, and because of that then dislocations could get generated. I hope you understand this point, right, that the dislocations are getting generated at the interface. That means at the interface there is some residual stress, and residual stress can get generated only when they do not get released. Okay. That is why the interface is quite adherent, and because of this adherence the residual stress is basically remaining there, and that leads to generation of such dislocations. Okay. Now, if you look at this particular image, here actually a line scan has been done to find out the composition of the different elements being present, which has been shown here. You can see nickel is present there. That means these are two actually copper particles, and in between, in this case basically copper grains, and in between the copper grains there are some CNTs being present, and here also what we are seeing here, presence of nickel. That means nickel is there, which improves the weightability. Now, some interesting features you are seeing in D, E and F. What are those? There were, if you remember, in the SEM image of the carbon nanotube particles, you can see here that carbon nanotube is this one, okay, but then nickel nanoparticles have been deposited on the surface of the carbon nanotube. However, it is not very uniform, or the whole surface of carbon nanotube is not completely covered by this nickel nanoparticle deposition, and the result of that, or the effect of that, you can see in this particular TEM image. So, you can see wherever they were exposed CNT, in those areas Cu2O is now forming. So, during ball milling or for some other reason, some oxide some oxygen entrapment could take place in the powder particle mixtures, and ultimately that is leading to formation of this kind of copper nanoparticles in the along the vicinity of the interface. Okay. So, that is what is happening here. So, ultimately now once we understand the microstructure and then we understand how is the interface, now let us look at the mechanical properties. How is the mechanical property of this composite material? Okay. Then only the whole cycle gets complete, right. Material has been processed. Okay. After processing, what is the effect of that processing on the microstructure, and now you want to look at the mechanical properties, that what is the effect of that particular microstructure on the mechanical property of the components or the parts or the specimens which have been synthesized or fabricated. So, what we are seeing here is that typical tensile plots, so this black line, so and this is stress versus strain versus stress plot. I mean, so what you are seeing here, this black line, what you are seeing, that is coming from pure copper. Okay. So, pure copper has been spark plasma sintered. So, all these specimens have been basically spark plasma sintered and then cold rolled, and then it has been mechanically tested. So, this one is for pure copper. You can see clearly copper is a ductile material. So, it shows nice elongation as it tensile tested. Okay. Now, if you compare with this RCU, what you see, RCU is basically rolled CU, pure copper rolled. Okay. Now, you can see here, because of rolling the density increases, and it also would lead to some amount of increase in dislocation density because of cold rolling, and that leads to, you can see clearly, increase in the strength, both UTS and yield strength and UTS. Both is increasing, both are increasing because of two reasons. One is cold rolling leads to better densification, also cold rolling leads to increase in the dislocation density in the material, and that is why you can see increase in the yield strength as well as UTS. Okay. Now, if you compare that with the first one, what you are seeing here, this let us compare with 1 volume percent nickel CNTCU. That means it is actually sintered, but not rolled. Okay. This 1 volume percent, this blue line. So, obviously, as it is CNT is there. So, if you compare with this one, okay, which is copper rolled, or here it is not rolled. So, let us say this one with copper sintered, okay, with this one which is copper 100% CNT. You can see obviously because of 100% CNT, there is fairly good increase in the strength, is not it? and what is losing here? Obviously, some amount of ductility is getting lost in the way, because of when you have CNT at the interface, there would be some amount of microporosities being present and other things could be happening, and that could lead to decrease in the ductility. But ultimately strength has been increased, and the strength gets further increased in this green line. You can see when it is rolled. So, this one is sintered only with CNT. Now, this one is sintered plus rolled with CNT, right. That means, once it is rolled, obviously that even lead to increase in more strength because of higher densification. And you can see here similarly, when it goes to 2 volume percent, obviously because of the agglomeration problem, and when there is agglomeration in between those agglomerated nanoparticles, or in this case agglomerated carbon nanotubes, there will be entrapped porosities. Okay. And these entrapped porosities would lead to decrease in strength, because ultimately there from those defect points fracture would initiate, right, or failure would initiate. So, that is why you see actually when you have 2 or 2 volume percent CNT, in both cases it is rolled or not rolled, does not matter. In both cases you can see the strength has been decreased, and that you can see here as well. If you look at this particular histogram plots, so you can see this is for pure copper, and then 1 volume percent CNT copper, and then 2 volume percent CNT copper. So, in all cases you can see from UTS has been increased after cold rolling. You can see UTS has increased after cold rolling. Now, if you compare with pure copper and copper CNT, obviously there is increase in again both yield strength and UTS, and then when it comes to 2 volume percent, because of agglomeration problem, again you can see there is certain decrease in the value of yield strength and UTS, and that particular property those ultimately gets reflected in the fracture surface as well. If you do the fractography, what you are seeing here in these first cases A and B both are actually 1 volume percent CNT, and then C and D are 2 volume percent. So, obviously you can see because of you can see here, this is the graph, this is the line. Okay. So, you can see it shows fairly good ductility, and you can see also these dimples in on the fracture surface. So, that actually signifies that it has fairly good ductility, and obviously some CNT clusters are still being observed. However, and this is the high magnification image which shows the carbon nanotubes with higher diameter. That means these carbon nanotubes are actually having certain amount of weightability with nickel and then copper. However, the scenario gets changed when it is 2 volume percent. That means you can see here there is less amount of dimples, and you can see some amount of cleavages as well. Okay. Some amount of cleavage failures as well, and those are coming because of the poor ductility, higher amount of porosity when you have 2 volume percent CNT. All right. So, ultimately the conclusion from this work, we can see that acid treated CNTs were partially covered with nickel coating through electroless deposition, and nickel CNT copper composites were fabricated through ball milling, SPS and subsequent cold drilling. Compared with uncoated CNTs, distribution is much more uniform in nickel CNT, and after rolling the distribution becomes aligned with to the rolling direction, and rolling leads to ultimately improvement in UTS and yield strength as well. And as the content of nickel CNT increased from 1 to 2, once the CNT amount is increased from 1 to 2%, obviously UTS is getting decreased because of agglomeration problem. Okay. So, you can see there are a lot of things are happening here. Once you are using nanoparticles as reinforcement, and then you are trying to improve the weightability by doing different treatments like functionalization or coating with some metallic coating, and then how those things are affecting the mechanical properties, how those are affecting the microstructure, and how actually you should actually judge those things. I think this is a fairly good example to understand those different points. Now, let us quickly go into another example, as I mentioned earlier, on ZrO2 NB CMC. So, here the important thing is this, that you see here the matrix is ceramic. Okay. The matrix is ceramic, which has been reinforced with ductile reinforcement here, which is niobium. Okay. So, how it has been made? YSG has been used, that means yttria stabilized zirconia, which is tetragonal structure, and then niobium powder has been milled for 4 hours, and then those have been mixed together, and then you can see here those have been mixed together by ball milling. So, the zirconia particles and milled niobium, they have been milled together in a suspension, like so basically it is wet milling, and then once it is dried, after drying the powder mixture, there has been actually ground in agate mortar, and then those powder particle mixtures have been consolidated or sintered by hot pressing. So, in this case the sintering technique is hot pressing. Okay. The sintering parameters have been mentioned here, what temperature, pressure and all those things. I am not going to that. Now, if you look at the initial particle microstructure, these are niobium particles. After ball milling, you can see those become flaky. Obviously, after ball milling, because of plastic deformation in between the balls, the powder particles morphology becomes flaky, as you can see here. Okay. In the XRD, you can see, so this is for the without ball milling, the first one, and the second one is after ball milling. So, you can see there is obviously peak broadening is taking place, and also another important point you are seeing here is that the powder particles are getting quite textured after ball milling. So, you can see here that it is basically 200 or 100 reflections are parallel to the powder surface. Okay. And why these things are happening? This is happening because of the ball milling. As there is ball milling, the ball milling leads to increase in defect density, increase in dislocation density, and that is why and you can see here, because of straining and because of some amount of decrease in grain size, there is peak broadening, and ball milling also leads to this kind of preferred orientation or texture. Okay. Now, after consolidation, after hot pressing, what you are seeing here in this particular image, that these niobium particles, these white kind of particles are actually nicely distributed on the surface. I mean everywhere inside the matrix is ZrO2. You can see there is not porosity, not much porosity, and in fact porosities are almost absent, and what you are seeing, those niobium particles are uniformly distributed. Not only that, those have been, you can see here, actually those particles have been oriented normal to the hot pressing direction. Okay. And the interface, yes, you want to see the interface, that is what we want to do. So, you can see here this quite a rough interface in between ZrO2 particle or ZrO2 grain and niobium grain, and there is not any fixed relationship at the interface. Somewhere it is coherent, somewhere it is incoherent. So, basically you can call this particular interface is incoherent interface. Okay. And the interface is also quite clean also, in terms of there is no formation of any other oxides. I mean there is ZrO2, there is a niobium. So, maybe some suboxides or complex oxides could have formed, which is not really forming here, because ZrO2 is quite stable. Okay. So, that is the that is what you understand from this particular TM image. Now, the next thing, which is again very important, now the ultimate aim was here to improve toughness, fracture toughness of ZrO2, right. I mean all ceramic matrix composites which are synthesized, the idea is to improve fracture toughness. In this case, metallic ductile particles were used as reinforcement to improve the fracture toughness. So, let us see the result. This is ZrO2, pure ZrO2, okay, no niobium. So, you can see here the fracture resistance does not really it is not really stable with it. Okay. With crack extension, fracture resistance is kind of gets linear. However, here you can see here that first of all the fracture toughness is quite higher than the pure ZrO2. The composite is having better fracture toughness. Also, you can see there is a rising R curve with a maximum crack growth resistance almost twice the initial value. So, you can start with, we are starting with around 8 and it is almost becoming 16. So, that means there is a rising R value or fracture resistance actually increases, okay, with crack extension. And why this thing is happening? this kind of phenomenon, why there is improvement in fracture toughness, let us understand in the next slide. So, here actually what kind of different phenomena is taking place to improve fracture toughness are nicely described. So, you see there are few things that are happening. The first thing what we are seeing here is the delamination. That is the classic way of improving fracture toughness. Okay. It allows certain amount of delamination, but it is not completely delaminated. You see, okay, it is delaminated and then crack has, there is a branching kind of taking place in the crack. Okay. But then this portion, if you look at this portion, here there is good amount of plastic deformation in the niobium particle. You can see here there is no delamination, the interface is quite adherent. You can see there is another crack is coming from this side, okay, and this crack actually gets bridged in this particle. Okay. So, you can see delamination first thing or decohesion at the interface is happening. You are also seeing some amount of plastic deformation which is improving fracture toughness. Along with that, there is bridging is also happening here. Okay. You can see in this particular image, this niobium particle, there is a ridge formation, which basically signifies plastic deformation in this particle. Okay. Along with that, you also see there is delamination. So, what is happening? Partial delamination along with partial plastic deformation. So, which is like a unique combination in order to improve fracture toughness. You are seeing both, you are seeing delamination, not complete delamination, partial delamination along with improvement or basically some amount of partial amount of plastic deformation. You are also seeing here this kind of complete kind of brittle failure because of better interfacial bonding here. Now, the particle itself, the niobium particle itself is getting fractured. Okay. So, all these different kind of mechanisms are playing role in improving the fracture toughness. So, ultimately the major toughening mechanism is the plastic deformation of niobium particles that have been partially debonded. So, partial debonding along with plastic deformation, and that is what is required. So, partial interfacial debonding allows the reinforcement to neck, while the remaining interface area in contact with the matrix allow an effective load transfer to the reinforcement. Ideal situation. Okay. You are having some amount of delamination, you are having some amount of plastic deformation. At the same time, the load is also getting transferred because it is not completely delaminated. Okay. So, that is what ideally we want to happen. Okay. So, so in this class I have discussed about copper CNT composite and ZrO2 niobium composite. One is metallic, other one is ceramic, and in both cases how the processing is playing role in making the microstructure and ultimately making the interface, and how that is leading to change in their mechanical properties. I think that we try to understand. Okay. So, with that I would conclude today's class and I will meet you in the next class. Thank you.